All right, let's dive in. We're going to pull back the curtain on the hidden science that powers, well, pretty much everything you use today, optoelectronics. It's this incredible field where we figured out how to make light and electricity talk to each other, all inside a single tiny chip.
So let's start with a question. Think about the internet, the fiber optic cables bringing this to you right now, and then think about lasers. And now think about solar panels on a roof. What do those three things possibly have in common? They seem completely different, right? Well, it turns out they all rely on the exact same fundamental and totally revolutionary technology.
So how did we get here? Here's our game plan. We're going to start with the big idea, what is the stuff? Then we're going to shrink all the way down to the atomic level to see how it really works. After that, we'll look at the big engineering breakthrough that made it all practical. Then we'll push things into the quantum realm, and finally, we'll open up the physicist's toolkit that ties it all together.
Okay, Section 1. What is optoelectronics? At its core, it's pretty simple. It's the science and engineering behind devices that do two things, and they do them really well. They turn light into electricity, and they turn electricity back into light. That's it. It's the ultimate translator between the world of photons and the world of electrons.
And the secret ingredient, the magic material that makes this all possible, it's something called a semiconductor. Think of a material like gallium arsenide. Now, it's not a great conductor, but it's not an insulator either. It's in this perfect sweet spot in between. And that special property lets us control the flow of electricity with incredible precision. It really is the perfect stage for this dance between light and matter.
So, let's zoom in. Way in, we're going right inside that semiconductor chip. What is actually happening at the level of atoms when light smacks into it? Because this is where the magic really begins.
Okay, so imagine the before state. In a regular, happy semiconductor crystal, all the electrons are locked into place. They're busy holding hands with the atoms, forming the structure of the crystal. Physicists call this the valence band. The key thing to remember is they can't move. They're stuck. So no electricity can flow. It's basically an insulator at this point.
But then, bam, a photon, a little particle of light, comes flying in and smashes into the crystal. Now, if this photon has enough energy, enough juice to break one of those electron bonds, it knocks an electron totally free. So now you've got this free electron roaming around the material, and it leaves behind a little empty spot, a vacancy that we call a hole. And with a free electron and a mobile hole, boom, you can create an electrical current.
And here's the absolute crucial point. This whole process works in reverse. It's a two-way street. You can have light come in and create a current. That's how a solar cell or a camera sensor works. Or you can inject a current, creating a bunch of free electrons and holes. And when one of those free electrons finds an empty hole and falls back into it, it releases all its extra energy by spitting out a brand new photon. And that is light emission. It's the basic principle behind every single LED and laser you've ever seen. Okay, so understanding that principle is one thing, but actually making it useful, that's a whole different ballgame. The first devices based on this were, honestly, pretty terrible. So how did engineers turn this cool physics trick into a technology that changed the world? Well, that brings us to a massive breakthrough.
You see, the big problem was efficiency. The very first semiconductor lasers were just awful. They were so inefficient, you had to cool them with liquid nitrogen just to get them to work at all. And even then, they could only fire in these tiny little pulses. They were basically a lab curiosity, not something you could put in a Blu-ray player.
The answer, the brilliant solution, was something called the heterojunction. And this is just a genius piece of engineering. What you do is you grow a super thin layer of one semiconductor material right on top of another one with slightly different properties. So you end up creating this sandwich. And that interface, that boundary between the two materials, acts like a perfectly designed little corral, specifically designed to trap electrons and holes. And here's how that amazing trick works. You pump electrons and holes into that thin middle layer. The heterojunction barriers on either side act like walls that can't escape. But here's the really clever part. The material in the middle is also designed to trap the light. So you're forcing both the particles and the photons into the same tiny space. We call this double confinement, and it massively increases the odds that an electron will find a hole and create a photon. And this is what it actually looks like. You can see that super thin gallium arsenide layer, the active region, right in the middle. That's where all the action is. And it's sandwiched between those other layers of alka gas. That structure creates an energy well that the electrons and holes fall into and can't get out of, and at the same time, it traps the light. Just brilliant.
And the impact of this one idea, I mean, it's almost impossible to overstate. This double confinement made lasers so incredibly efficient that they could finally run continuously without melting at room temperature. This single innovation is what made fiber optic communications, CD players, laser pointers, pretty much all of it, possible.
But of course, scientists and engineers didn't stop there. They never do. They took this whole idea of a heterojunction and pushed it to its absolute logical extreme. They started shrinking that central layer down and down and down until it got so thin it entered the wonderfully weird world of quantum mechanics. And that brings us to the quantum well. Now, that active layer, that trap in the middle, is so incredibly thin, we're talking just a few atoms thick. It's practically a two-dimensional space. And when you confine an electron to a space that small, normal physics just breaks. It stops acting like a little particle and starts acting like a wave, and its behavior is now governed entirely by the bizarre rules of quantum mechanics.
And that changes absolutely everything. See, in a normal bulk material, an electron can have pretty much any energy it wants. But inside a quantum well, it's only allowed to have specific, discrete energy levels, kind of like the rungs on a ladder. It can be on this rung or that rung, but nowhere in between. And the best part? We get to build the ladder. By changing how thick we make the well, we can actually change those energy levels. We're not just using a material anymore, we are literally engineering its quantum physics by design.
And this is the result. Modern, high-performance lasers are all built around this quantum well principle. It gives engineers an unbelievable level of control, which leads to lasers that use way less power and can be tuned to produce incredibly pure, specific colors of light.
As S.L. Chuang, the author of our source text here, puts it, we've basically created artificial materials where we can directly see and control quantum effects. It's not just theory anymore. It's like we've built a tiny, custom physics lab right inside the chip itself, just to get the perfect performance we need.
So, what does it actually take to design one of these incredible devices? Well, it's not just one area of physics. It's more like a symphony, where a whole bunch of different principles have to come together and work in harmony. Let's take a look at the toolkit.
This diagram really lays it all out. To build one of these things, you have to be a master of a whole bunch of different fields. You need Maxwell's equations to understand how the light behaves. You need the Schrödinger equation to understand the quantum mechanics of the electrons. And you need semiconductor theory to understand how the current flows. A device physicist has to juggle all of these concepts at once to make the chips that power our modern world.
So, let's just quickly run through what we've learned. We started with optoelectronics, that bridge between electricity and light. We saw that it's all built on the foundation of semiconductors. Then came the heterojunction, the huge breakthrough that used double confinement to trap both particles and light, making devices efficient for the first time. And finally, by pushing that idea to its limit, we got quantum wells, which let us engineer quantum physics right into a chip.
And that really leaves us with a fascinating final thought. We've gone from just using materials we find in nature to literally building new materials, atom by atom, to control the fundamental laws of physics on a chip. We've already harnessed that power for lasers and detectors and the internet, but what comes next? What other incredible technologies will be unlocked now that our toolkit includes the ability to engineer reality itself at the quantum scale?